All right, 6.4 is ratios, proportions, and proportional reasoning. So to start with, I want to talk about what a ratio is. A ratio has 3 different ways of being written. You could actually write it as A colon B, A over B, or you could actually even write it as A and the word to and the word B. All of these are read verbally as A to B. Okay, it's a comparison of 2 things. There's 2 ways to do the comparison. One way to do the comparison is part to whole. For example, if there's 15 students and 7 of them make A's, the ratio of the part to the whole would be 7 to 15. Okay, the part of the class that made A's compared to the whole class. Part to part is a comparison of people who do something compared to those who do not do something. All right, so a part to part, 15 students, 7 of them make A's, the ratio would be 7 to 8. That is the ratio of A's to non-A's in the class. So sometimes you'll hear things done with a ratio, right? Your ratio of boys to girls. You guys talk about this on this campus a lot, don't you? Ratio of boys to girls, right? But you could also talk about the ratio of girls to the entire student population. Ratio of boys to girls would be part to part. Ratio of girls to the entire student population would be the part to whole. Okay? So we use ratio verbally in both of those ways frequently. All right, so here's an example. If the ratio of boys to girls in a class is 2 to 3, okay, so that's boys to girls, what is the ratio of boys to the students in the class?
Are you asking us if it's part to whole or part to part?
No, but you do have to recognize which one it is in order to keep going in the problem. So let's start there, Ashley. Is it part to part or part to whole to start with? Is it? I think it's part to part to start with because it says the ratio of boys to girls. So, in fact, I'm going to write that down so that we're real clear on this. Boys to girls. So the ratio of boys to girls is 2 to 3. What I want is I want a ratio of the boys to the class as a whole. Any thoughts?
2 to 5.
It would be 2 to 5, Lydia. How did you get 2 to 5?
Because there's 2 of the boys and 3 of the girls, so you add them together to have the entire class.
Right. And we recognize this is a ratio, so we probably have more than 5 kids.
Yeah.
But the process reduces to that no matter how many kids you had. So if we have, for every 2 boys, we have 3 girls, then for every 2 boys, we have 5 children. Right? So it's almost like the denominator becomes the 2 values added together, right? That's what you're seeing happen when you go in that direction. Now, example 2 has you go in the other direction. 3 to 7, or 3/7 of the class are girls. So in this example, we actually start with girls compared to the class. So how do we get the ratio of girls to boys? We would do a subtraction. Last time we did addition, so this would be 3 to 4. For every 3 girls, there's 4 boys. That'd be better, wouldn't it? Yes. And in essence, exactly what you're doing. You're taking this 7 and you're saying 7 minus 3. That's the 4 of the boys that you had. All right, a proportion is simply a statement that 2 ratios are equal. Okay? So ratio on the left, ratio on the right, we put equal sign between. Lo and behold, we have a proportion. Theorem 620 says that if we have a proportion A over B equals to C over D, that this is in fact a proportion if and only if we're able to cross multiply and get them equal. And that's sort of a hangover from what we did in the last section, right, in 6.3, where we were looking at when fractions are equal, right? Because ratios are fractions, so this should make sense that this would work. So we're able to use this feature oftentimes to actually solve a proportion for a given quantity. That's how we use it usually. Theorem 6.1 has a very similar feel to it, except that you don't see the cross multiplication. So it looks like we've got A over B on the left, C over D on the right. What happens in this fraction down here? Yeah, we just turn them upside down, right? But notice, if we just turn fractions upside down and we cross the multiply them like that, don't we still get the same cross multiplication that we got up here in this problem? Yeah, we do. if we cross multiply, we still get AD equals BC. So it's perfectly legitimate to flip the fractions upside down and they will still be in proportion form. What's happening down here in theorem 6.2? A over B to C over D, and it becomes A over C to B over D. What changed? Huh?
C and B.
The C and the B, right? These two switched locations, didn't they? But does it matter? Not when you cross multiply, right? When I cross multiply, I still get AD equals BC. Yes, Beth?
Why would you do that?
What they're wanting to show you, and this will happen once we work in this section and in another section in chapter 7, is that as you work with proportions, there's more than one right way to set things up. And the reason there's more than one right way to set things up is because we have this cross multiplication feature going on. So sometimes, for instance, an example I have, I don't remember if it's in this lesson or later, is a comparison of like this, the number of miles it actually is to drive places and the inches that represents on a map. So some people would actually look at everything on the left-hand side being the inches representation and everything on the right-hand side being the real-life miles representation. Whereas some people would look at this differently, and they would actually set it up so that the miles were on top and the inches were on bottom. And it all works out the same way because when we do the cross multiplication, we get the same features. All right, so here's an example of one, and we're going to do just what we're talking about here, Beth, okay? Jim found out after working 9 months he has 6 days of vacation time. Evidently, Jim has not been very on top of it because I would have gone into the job knowing that if it were me. He wants to know how many days he gets per year. Okay? So what we're able to do is we're able to set this up in a proportion. Now I want to make very clear to you guys this. There are other ways to solve things besides proportions. Proportions, however, are really, really handy, and conceptually they're really easy to work with for kids. So throw out everything you want to think about creating some equation in some other way or working the problem in some other way. This section, you're only allowed to work with proportions, okay? So if you solve the question in some other way, you just might as well have said goodbye to the points because the point of this section is proportions, all right? So what are we comparing in this problem? There's several things. What are we comparing? Somebody give me one. Months of working, right, to days of vacation, okay? What else are we comparing? I think we're comparing lengths, right? We're comparing the length of him working 9 months compared to the length of him working a whole year. Are you with me on that? There's 2 different lengths of time we're actually looking at. The length of time is a comparison. So I'm going to set it up in 2 ways just to show an example of what Beth was asking about of why does this matter that I can switch this all around. One way to set this up is to talk about a day to month comparison. Okay, like this, as a ratio. So, how many days does he get right now? How many does he have? 6 days. How long does he want? I'll write days in here so we're clear. How many months has he worked? 9. And our comparison that we're comparing this to is what? X days, because that's what we're looking for, over 12 months. Good. Make sure that you're still in the same unit. We don't want the number 1 for years. We want months. Okay? So we can cross multiply to solve this, right? I don't need to keep using the words days and months everywhere. I just put them in there so we can keep everything clear that we put them in the right place for the moment. So if I multiply across my diagonals now, what do I get? 9x. Hannah did the easy one. What's the other one? Is it 72? Excellent. Now what? Divide by 9. So what is x? 8 what? 8 days. Make sure you put units on it because it doesn't really make sense without them. Now let me show you another way we could have set this up that will yield the exact same answer, Beth. We could have set it up so that everything on the left is days and everything on the right is months. So how many days do I have of vacation right now? 6 days. And I want to know how many days I will have at the end of the year, presuming I don't use them. And I can compare that to, well, how many months have I worked? 9 months. And how many months will I work by the end of the year? 12 months. But lo and behold, look what happens when I cross multiply. It's the same thing. So there's two distinctly different ways to set this up that yield the same result, because it depends on how we're making the comparison. Does that help you to see why those theorems are in there? Okay.
Why can't we simplify 6 and 9 first?
You could. You could. Yeah, if you wanted to simplify, Ashley's question is, why couldn't we take this 6 and this 9 and simplify? Or for that matter, down here, you could take the 9 and the 12 and simplify. You could. It's really not a lot of work either way to do it. So either to do that and simplify or to simplify at the end. Yeah, either way's fine. Oh, here's my map question. I did remember well. On a city map, a rectangular park has a length of 4 inches. If the actual length and width of the park are 500 feet and 300 feet respectively, how wide is the park on the map? All right, so there are two comparisons being made. What are they? Length and width. What else? Inches and feet, like the real life size feet to the map size inches, right? The map compared to real life. All right, so let's talk about how we want to set up our ratios. How do you want to do your ratios? Inches to feet. Abby says she wants to put inches on top and feet on bottom. Okay, so if that's what we're going to do, that means that we have to divvy up our length versus our width. So I'll make my length on the left and my width on the right. Is everybody following that? Okay. So what is the length of the park in inches on that map? 4. What is the length in real life? 500. What is the width on the map? We don't know, so we'll call it X, or whatever letter you like would be fine. What's the width in real life? 300 feet. And then what? You can cross multiply. So one way I get 500X. What's the other one? 1,200. And then I would divide by 500. What does X equal? 2.4. So it'd be 2.4 inches. Very good.
Would you want us to put that into a fraction?
That's a good question. So think about how you would report that to somebody in real life. Would 2.4 work? Yes, it would. You could say 2 and 2/5. 0.4 is actually 2/5. That'd be okay, but 2.4 is also okay. So you want to report it in a way that would make sense. For instance, if you turned that into an improper fraction, that wouldn't be very reasonable in real life. I mean, people don't talk like that, right? They would look at you and say, what are you talking? I mean, they just would have this, they'd glaze over. They might glaze over when you talk to them about math anyway, but they glaze over. So 2.4 is a very reasonable way to express that. Okay, we have Sheila and Dora, and then we have Rattlesnake School. All right, let me set up Sheila and Dora, because this is an interesting setup that you're going to see on your homework. And then we'll stop, and you guys can solve it on your own, and I'll solve it later and post it. Sheila and Dora work 3.5 hours and 4.5 hours respectively on a programming project. They're paid a total of $176 for the project. Question is, how much did each of them earn if they're paid at the same rate? Hopefully you look at that and you don't say, well, they're just going to divide it in half, right? That wouldn't somehow be fair, right? The person who worked more should get paid more. That's what this problem is getting at. So what are we comparing? How much they worked to how much they got paid. Good. So I'm going to put work over pay. Does that sound okay? So the work is sort of easy, right? I mean, we would just compare, well, one of them worked 3.5, the other one worked 4.5. The problem is, I don't know how much either one of them was paid. Do you guys see that? So I'm going to suggest that we write this down as Sheila on the left and the total amount on the right. I'll show you another way to set it up too if you don't like this one, but how much did Sheila work? 3.5. How much did Sheila get paid? We don't know. X. Right? How much was total amount of time worked? 8. What was the total pay? Would this find how much Sheila worked or how much Sheila was paid? Yeah. How could I then find how much Dora was paid? Subtract it from the 176. So this is one option. Let me show you option number 2. To be honest, I think option number 1, it makes the most sense, and you'll like it the best, but some of you might not. We could compare Sheila and Dora. Sheila would still look like 3.5 compared to X. Dora would look like 4.5. But I don't really want to put Y down here. But here's what I could put. If Sheila makes X dollars, then Dora makes 176 minus X. And that's how you can take care of the fact that you know the total amount, but still write them as 2 separate fractions. The downfall, not downfall, but the more difficult thing working here is that when I do this cross multiplication, I've got to distribute, and I'm still working them with fractions in the middle of that because they're mixed numbers. It's not bad, but it's just another way of thinking about it.